Welcome to another unit in this workbook statistics. This time I'm going to talk about measures of dispersion. While for measures of central tendency we also can calculate statistics for nominal data, with measures of distribution we need some information about the order underlying the data. So the first measures of distribution we can calculate require at least ordinally scaled data. And here the easiest version would be the range which is simply largest minus smallest value, telling us which scope the whole data set actually covers. The next one is quite similar to the range, but it does not include the whole data set, but something like the middle 50%. That's the interquartile range. The interquartile range, that's just the difference between third and first quartile. And we see here, that's the lowest 25%, that's the lowest 75%. So this difference describes the scope of the middle 50% of all the data. Well, the interesting thing about those two statistics is we can also really nicely illustrate them graphically. Because if we take a look at a classical box plot, we have the distance from antenna to antenna, that's the range, that's the whole scope of our data set, and we have the height of the box, that's the interquartile range, that's the middle 50% of the data set. So that's something which works for ordinal data. If we have more information on our data, if we have, scaled data with a much higher scale level, like metric data, we can also calculate much more sophisticated statistics. That's something I want to go into in this part, in the next slide. Here we can, however, first differentiate between theoretical, uncorrected values, census data and sample data. Well, what's the difference? Census data means that our sample includes all possible observations. So the whole population is the sample, or rather there's no difference between sample and population. Well, sample itself is usually just a subgroup of the whole population, and theoretical data is different from this, and this is best illustrated with an example of a dice. If we take a classical six-sided dice, every six-sided dice has an expected value of 3.5. That's just the average of the 6 different sides, so it's the average of 1, 2, 3, 4, 5, and 6. That's 3.5, and that's the same for each and every six-sided dice with values from 1 to 6. However, if I throw the dice for a certain amount of times and I calculate the average, not necessarily will I always get 3.5. That's because in this case I'm working with the arithmetic mean and with sample data. And the same thing which holds for the average, for the arithmetic mean, also holds for variance and standard deviation and all the statistics built in one way or another on them. So we also have for each dice a fixed variance, a fixed standard deviation, but if we roll the dice, if we actually calculate sample data, we might get a different value for the standard deviation or for the variance. So in practical terms, if we work out with theoretical data, we use an uncorrected version. If we work with sample data, we're going to use a corrected version of the statistics. In some cases, we also differentiate simply in theoretical variance, sample variance, theoretical standard deviation, sample standard deviation. Well, with those introducing words, let's start with the variance. The variance looks like this, and if we closely look, we can easily explain what the variance actually is. Here we have the deviation from the mean. this deviation is squared. And we do this for all data points, and then we're going to add this up. So it's the sum of the squared deviations. Not just the sum, because we're dividing the sum by the number of observations, which makes it the average. So it's the average squared deviation from the mean. Well, that's nice to know. We could also interpret this from a geometrical point of view, but I think this would be beyond the scope of this textbook. However, well, the problem with the variance is this is a data point measured in the dimension of certain, well, whatever it is about. For example, if this is the height of a person, the mean is also height of the person. But if we square this, we actually have height, for example, it's with meters, squared. So it's square meters. Square meters is very hard to interpret correctly if we talk about height of people. Well, that's why instead of the variance, be it the corrected or the uncorrected version, we're going to use instead the standard deviation. The standard deviation, we're going to see this on the next slide, is simply the square root of the variance. Square root takes care of the problem with the units. As I said, the unit here is square meters with height. If I switch to the standard deviation, take the square root thereof, we would again have as a unit for the standard deviation meters. So it makes much more sense to interpret the variance, the standard deviation, then it makes sense to interpret the variance. However, before we switch to the standard deviation, one final comment on the variance. We could use this way of calculating the variance, or we could use a respective theorem to make our life a bit easier, and that's this one here. This would mean instead of calculating all these terms, we can take simply our squared observations. So instead of taking the average of all observations, we just square each of our data points. And then of those squared values, we're calculating the average. And from this average, we're going to subtract the squared arithmetic mean or the squared expected value. That's a different way of calculating the variance. Of course, this only works for the uncorrected version, the theoretical version. If we work with sample data, we need to correct this. So instead of 1 divided by n, we're going to use 1 divided by n minus 1. We have to multiply this part here with this correction factor. So in other words, gets rid of this part and replaces it with this part. That's what the correction factor is all about. But usually this is a much easier way to calculate the variance, or much quicker way to calculate the variance than this formula. Well, as I said, instead of the variance, we're usually going to use the standard deviation, which is just the square root of the variance. This has the advantage as the same unit as all of our data points. So we can actually use this to describe how far away from our data we actually are. And similarly, works with uncorrected data, with theoretical data, works with sample data in exactly the same way. The neat thing about standard deviations is it tells me quite a lot about my data. If my data is more or less normally distributed, that's why we're using this normal distribution curve here, and this is my average or my mean, I know that plus minus 1 standard deviation covers more than 2/3 of my data points. So here it's the 68.27%. Plus minus, so mean plus minus 2 standard deviations covers more than 95%. That's actually also one of the many reasons why we use margins of errors of 5%. That's more or less plus minus 2 standard deviations. And finally, plus minus 3 standard deviations is with almost certainty, it's with 99.73% of all data points which are covered in this interval. So if I know my data is more or less normal, and I know the mean, and I know the standard deviation, I have a very good grasp about the distribution, about how many observations fall into which interval. That's a neat thing to know. Well, the standard deviation certainly has its benefits, but there's also still one significant problem. And as I said, it's still in the unit of our data points. That might not be a problem if I want to compare the height of, well, group of people 1, group of people 2. The height of Germans with the height of Dutch people. It's the same unit. But what if I want to know which of the data set fluctuates more, the height or the weight of the German people? There I'm comparing meters with kilograms. So what could I do in this case? In this case, we have the so-called coefficient of variation. The coefficient of variation has the distinct advantage that it's unitless. Well, how do we get this? We take the standard deviation, we divide this by the average. Standard deviation is in the unit of our data set. The average is in the unit of our data set. So the two units actually cancel each other out, giving us a unitless statistic. Unitless statistic, which exists for uncorrected theoretical data in the same way as it exists for sample data. Well, if it's a unitless statistic, we could just calculate this, for example, for height. We can calculate this for weight. And then we can compare these two variations or two statistics. Because, well, if the variation, the dispersion, is larger with weight than it is with height, meaning if the coefficient of variation is larger for weight than it is for height, then we know, independent of the units, that weight fluctuates much more strongly than height does. This wouldn't be possible with either of the other statistics we earlier discussed. So that's actually a pretty neat thing if you want to compare data, if you want to compare fluctuation of data across variables, across data sets. Well, that's then everything there is I want to mention with regard to measures of dispersion. I hope you enjoyed this unit. I say goodbye and see you next time.